Good morning, everyone. Welcome to our tutorial session. In this talk, I'd like to introduce vision language pre-training, including the basics, enhanced representation, and the different training strategies. But before we dive into the details, let's also talk about what is vision language research and why should we care about it. So, vision language research is basically about how we can train a smart AI system that can have joint understanding of both image and text modalities. And there are multiple popular tasks in this community, such as visual question answering, referring expression, multimodal verification, image retrieval, and image captioning. So for example, for the VQA task, basically, given an input question, you need to answer this question based on the image input. For referring expressions, you need to identify the correct image region reflects your textual input. For multimodal verification, you need to judge whether your input statement is true or false. For image captioning, basically, you need to generate a natural language description of the input image. So why we care about vision and language? I think there are multiple reasons. First, this is really how we interact with and learn from the world. Vision is a large portion of how humans perceive information, and the language is a large portion of how humans communicate. And we believe a smart AI system should have the ability to perform well on both. If you see this picture on the bottom, we require the AI system to have good visual understanding, and then based on this capability, our AI system should also have good language understanding capability. So on the top, we can achieve the multimodal intelligence. Application-wise, vision and language research also has great potential for visually impaired people. The second reason is vision and language is also a scalable way to learn visual representations. Traditionally, state-of-the-art computer vision models, they rely on carefully annotated labels or bounding boxes for supervised learning. And recently, self-supervised learning is really popular, and it is a scalable way to learn image encoders. But the visual signal can be, the supervision signal can be weak. On the other hand, another line of work, OpenAI Clip or the Google Align, they have been using large-scale noisy image text pairs that can be crawled from the web. And they show by using these noisy image text pairs, high-quality visual representations can be learned. On the other hand, vision language also has great potential to enhance language representations. As the old saying says, a picture is worth 1,000 words. And in terms of this direction, there are some initial attempts, such as the vocalization paper, where each token is associated with a related image. In this year's NACO-based long paper, the topic is also about video aided unsupervised grammar induction. Finally, so it is just fun. If you see the OpenAI DALL-E blog, they can create images from the text, and it is really just unleash the power of AI system, unleash the creativity of AI system. You can so from the example on the right, you can imagine how creative the AI system is. So vision and language research naturally lies in the intersection of both computer vision and NLP community. And as can be seen here, the vision language community is actually not small from the accepted papers in CVPR last year. In the NLP conference, such as ACL last year, there is also a language grounding check. And we can see the community is also growing. So it is really an exciting field to work on. Then a natural follow-up question to ask is how can we perform vision and language research? So there are already tons of papers. Before 2019, there are many different topics, such as how we can do better bilinear pooling to fuse the multimodal vectors. There is also tons of paper to design all kinds of different attention. We can also incorporate object relations into multimodal fusion. We can also perform multi-step reasoning. We can also design neural modules for more interpretable compositional reasoning. So in the tutorial session last year, we have provided a comprehensive literature review and a tutorial on this topic. But in this year, really, we want to discuss a more advanced topic. That is about how we can perform large-scale transformer-based pre-training. So what is transformer? Transformer is basically about self-attention, and it was first proposed for NLP task, for example, machine translation, and later on it was popularized by BERT and the famous GPT-2 or GPT-3. Later on, it was extended to image generation, vision language pre-training, and now vision transformer is really popular, right? So transformer has been adopted for image classification, object detection, and so on. And in this talk, we are going to focus on transformer-based vision language pre-training. VLP models has really achieved great success. During the summer in 2019, roughly 2 years ago, it is really a summer of unrest because there are so many concurrent work being proposed. And the momentum has been kept on, and since then many more models have been proposed. So in this slide, I'm going to organize all these works into a tree. In the bottom, we have our pioneering work in NLP. For example, we have two-stream model, LexMod, VLP. We also have one-stream model, VLP, and the Uniter. And then based on this foundation, based on this pioneering work in NLP, there are work that are trying to do probing analysis. There are also work to use enhanced visual representation. People are also more and more interested in end-to-end pre-training. There are also many different training strategies being proposed, such as adversarial training, multitask learning, and so on. There are also many diverse applications, such as vision language navigation, novel object captioning, visual dialogue, and so on. VLP can also be used to learn visual representation or language feature. As the pre-trained models become larger and larger, model compression also becomes a central topic in order to deploy such models for real-life application. Robustness, causality, and fairness is also an emerging topic in this field. And by the end, we can also extend the VLP model for multilingual tasks. So in my talk, I'm going to mostly focus on the left part of the tree. And if we take a closer look at VQA, so from roughly 4 years ago, we have the BOTD, the famous BOTD paper, and spanning 4 years, the performance of VQA has improved from roughly 65 accuracy, and now is almost 80% accuracy. So it's almost 14 points improvement. And in this plot, I'm going to divide the VQA progress, the VQA curve here, into 4 stages. In the first stage, there's no pre-training work, and in the second stage, there are many concurrent work being proposed. And here we can see the performance of VQA model has been improved from 79 goes to 73.4. And then in the stage 3, the performance has been further enhanced. And nowadays in the stage 4, the highest performance has been 79 point something. So it's almost 80% accuracy. And I'm going to present all to walk you through how the accuracy has been increased, how vision language pre-training has helping the VQA system to have a better performance. By the end, I'm also like to discuss briefly about end-to-end pre-training, which is an emerging topic. Okay, let's first talk about stage 1. In this stage, I'm going to mainly focus on the famous BUTD paper and also the MCAN paper. Let's first see how a typical VQA system works. Given an input image and also a question, basically we need to do image feature extraction, and we also need to encode the question. Then we will do multimodal fusion, and then finally we will do answer prediction. For image feature extraction, we can either use grid feature or object-centric feature from the object detection, and many of the vision language work has been focused on the multimodal fusion part. So let's first introduce the BUTD paper, which is short for bottom-up and top-down attention. This is the winning entry to the 2017 VQA challenge. The high-level idea is basically the use of object-centric image representation from object detector. As you can see in the picture on the left, typically attention models operate on CNN feature corresponding to a uniform grid of equally sized image regions. But then in the BUTD paper, they propose to calculate attention at the level of objects and other salient image regions. Since its proposal, basically all the follow-up work has been using the BUTD feature. But in the BUTD paper itself, the multimodal fusion part, which is shown on the right, is pretty simple. So for the winning entry to VQA Challenge 2019, so the multimodal fusion part has been much enhanced through the so-called MCAN model, which is short for Modular Co-attention Network. This is already very close to the transformer model that is used for vision language pre-training. So basically, the authors have designed two kinds of transformer block. One is called self-attention, and another is called guided attention. And then the self-attention is used to model the interactions inside one modality. And then the self-attention module will first be used in each modality independently first. And then the guided attention will be used to fuse the information of two modalities. And these two kind of module can be stacked or in two different ways. So this is how the MCAN model perform multimodal fusion. And when the multimodal fusion part be plugged into the pipeline, for example, the question is encoded by GLOB and LSTM. So back then it's still LSTM. And the image feature is fast SAN as used in BUTD. And the multimodal fusion part is the transformer I introduced just now. And then through the pipeline, they can achieve very strong performance for the VQA task. So this is already very close to multimodal pre-training. And then I'm going to introduce how multimodal pre-training works. I will specifically use Uniter as a running example. So pre-training is basically about a two-stage training pipeline. We will first perform large-scale pre-training on large, noisy chip data, and then we will fine-tune on downstream task. And for the downstream task, typically the data is small, but it's clean and carefully labeled. The good thing about pre-training is that it usually has very good generalization ability. That is, once we have trained a large-scale model, it can be adopted for a wide range of downstream tasks. This is the framework of Uniter framework that I'm going to introduce in more detail. But before that, I'm going to introduce how. So what's the pre-training data? So the pre-training data in the Uniter paper, basically divided into two parts. One is the in-domain data, another is the out-of-domain pre-training data. And the conceptual captions has been widely used. And now there is even larger scale conceptual caption data. And in the industry lab, such as Google, Microsoft, there's already so in the scale of 100 million noisy image text pairs for vision language pre-training. And in the picture here, it shows one example of how a conceptual caption looks like. It basically is a cleaned version of the original alt text. So this is how the pre-training data look like. It's an image text pair. And then we are going to extract the image feature and also the language feature. For the visual part, basically we will have different bounding boxes detected, and each bounding box will corresponding to one image feature. And for the text part, we will do tokenization. Okay, UNITE is a one-stream model architecture, and specifically we will first have an image embedder. The image embedder is so first we use faster RCN to extract the visual feature for each region, and also we will encode the location feature for each region via a 7-dimensional vector. And both the visual and the location feature, they will fed through a fully connected layer. Then they will sum up and then go through another layer normalization layer. For the text embedding part is very similar. Basically, we will sum up both the token embedding and the positional embedding, then through a layer normalization layer. After the image embedder and the text embedder, then it will followed by a unified transformer. As to pre-training task, there are several pre-training tasks in UNITE. First, in MLM, which is also used in BERT, we will randomly mask some words and then try to recover the missing words to their original ones. Similarly, we could also do random masked region modeling. That is, we randomly mask some region and let the UNITE model to recover them. We will also do the so-called image text matching. That is, during pre-training, we will sample positive pair or negative pair of the image and the text, and then we will let the UNITE model to predict whether they are paired or not. In UNITE, there's also a specifically pre-training loss called word region alignment, implemented by optimal transport. After pre-training, the pre-trained model can be adopted to many different tasks, and the VQA is probably the most popular benchmark for vision language research. So for VQA, the question is the input text, and the model will predict the probability over all the possible answers from the embedding of the CLS token. And in practice, the binary cross-entropy loss we are used for model training. Visual entailment is involved from the natural language inference task from the NLP community, and it mainly tests the model's understanding of logical relationships between the image and the text. Basically, we also use the CLS representation to do a 3-way classification task. NLVR2, they require the model to predict true or false of a given natural language statement about a pair of image. So the task mainly has 2 input images as input. So in order to adopt UNITE for this task, we will pair each image with the input text, and then in this case we will have 2 CLS token embedding here, and then we will concatenate them together to predict the true or false. Visual common sense reasoning, they try to test AI model's ability to reason about common sense in the multi-choice setting. So the model is not only required to answer the question, but also they need to provide a rationale of why you choose this answer. For this type of multi-choice question, image and the questions they will be duplicated for every answer choice, and all the CLS token output will be used to predict a confidence score of the answer. For referring expression comprehension, basically given an image and a sentence or a phrase, we ask the model which object is being described. And in this case, we will need the model to predict the region is is the region pointed out by the green circle. So basically, the united model can be also adopted for this task. For image text retrieval, basically we need to predict which image is closest to your textual query, and on the other hand, we can also do textual retrieval. So this adoption can be very straightforward because it is very similar to the image text matching laws used in pre-training. And so in the pre-trained model, we find the united often learns very good local class modality alignment between the regions and the tokens. For example, in this case, man, child, puzzle, they do a good. So they have been doing a good job to align the region and the token. United has achieved a very strong performance back then, so they achieve a lot of SOTA performance. Besides the one-stream model, I'd like to also briefly mention another line of work, which is two-stream model. Basically, two transformer, they will be first used to encode two modalities independently first, and then a third transformer, which is responsible for co-attention, is stacked on top for multimodal fusion. Just now I have described all the discriminative tasks, but the VLP can be also used for image captioning, and for this purpose, an additional sequence-to-sequence attention mask is designed because they want to mimic the behavior of image captioning. Because for image captioning, this is a text generation task, and when you generate the next word, you can only see the words that you have been generated, but you cannot see the future words. So they have designed a specific sequence-to-sequence attention mask in this paper. Our VLP model has been very successful. So what do these kind of models have learned? In this ECCV paper, the authors have trying to do a careful probing analysis. What they have been trying to do is the following. First, they have been doing probing the multimodal fusion degree. They also tries to probe the modality importance through the CS token. They also tries to probe the visual co-reference and also the visual relations. At last, they also want to see how much linguistic knowledge has been encoded in the VLP pre-trained model. They basically tries to probe two kinds of vectors. One is the attention weight probing. Basically, we have for united base, we have 12 layers, and in each layer we have 12 heads. So by the end, we have 144 attention weights. So this will form a matrix. We can also probe in the embedding vector. So this is the high-level message in the probing paper. Basically, they find deeper layers, they will lead to more intertwined multimodal fusion. As to modality importance, they find the textual modality seems to be more important than the image modality. They also find there is a specific attention heads that are responsible for cross-modal interaction, for visual relation, and also the pre-trained VLP model. They also encode rich linguistic knowledge. So now we will go into the third stage of the VLP models. And in this part, I'm going to talk about VILA, Oscar, ERINE-VIL, and UNIMO. I will mainly discuss how these methods can be used to enhance the performance of the pioneering VLP models. So I'm going to first talk about adversarial training, how we can use adversarial training to enhance the performance of VLP model. So briefly recap, what is adversarial attack? As you can see from the image, so this is a famous image. Basically, neural networks, they are prone to label preserving adversarial examples. Given the image, if you just add a very small amount of adversarial perturbation, and the output from the neural network can be totally wrong. For the NLP side, it's the same. Even if you do some minor changes to your input question, but your answer can be totally different, which is not desired. So what is adversarial training? It's basically how we can utilize this adversarial example as additional training data. So the high-level spirit is like, what doesn't kill you makes you stronger. On one hand, we try to find the perturbations that maximize the empirical risk. And on the other hand, the model tries to make correct predictions on adversarial examples. So as shown in this equation, it's a minimax game. And then how adversarial training can be used for VLP purposes. Basically, in the VLP paper, they have been proposing 3 ingredients. First is adversarial pre-training plus fine-tuning. Second is perturbation in the embedding space. Third is they also propose an enhanced adversarial training algorithm. The first one is we do not only perform adversarial training in the fine-tuning stage, but also in the pre-training stage, in the hope that if we perform adversarial training in the pre-training stage, then we can have a better pre-trained model so that a uniform performance improvement can be achieved. Since we do not care about the actual crafted adversarial example, so adding perturbation in the embedding space is a more efficient way to perform adversarial training. As to the detailed adversarial training algorithm, as you can see from the objective, there are 3 parts. The first one is the L standard loss, which is the standard cross entropy loss on the clean data. Given the input image and a mascot, so this is for pre-training purposes, and a mascot caption, and the model need to predict what is the mascot token. So they will calculate the cross entropy between your predicted probability vector and your ground truth label. So the second loss is the cross entropy loss on adversarial embeddings. Basically, it tries to say, even if I add adversarial perturbation, but your label should still be the same. But this is not enough. We may not only need the label preserving, but also we hope the confidence score, the confidence level of the prediction between the clean data and the adversarial example can also be close. This can be captured by the KL divergence term. So as you can see, the probability vector in the middle is the standard one, and on the top and on the bottom are 2 probability vectors predicted by adding adversarial perturbations on 2 modalities. And we want to use the KL divergence to measure the closeness between the corresponding 2 probability distributions, and we hope they should be close. So enable to let adversarial training for large scale pre-training and also promote diverse adversaries. They have designed the algorithm like this. First, they will perform perturbation update while PGD projected gradient descent. And then through multiple steps of PGD, they can accumulate the parameter gradient for free, so that in the outer for loop, they can do parameter update through stochastic gradient descent. Back then, VLP has established a new SOTA on all the tasks that has been being considered. Especially on the VCR task, it can provide almost a 3-point improvement. They will also be trying the image text retrieval and the referring expression tasks. In the ablation study, they show adversarial pre-training and fine-tuning. They both contribute to performance boost. In their paper, they mainly focus on United, but they also show VLP can be applied to any other VLP model, for example, LexMod. So this figure is interesting as it shows once your adversarial pre-training has been turned on, the performance has been improving. So it's a very good signal to say adversarial training can be an effective way to enhance your model performance, also during the pre-training stage. Besides performing adversarial training, another way that can be used to enhance the performance is to use object tag as the anchor points to align image regions with what the embeddings of the pre-trained language model. So as can be seen in this picture, the word semantic space can be more representative than image regional features. And specifically in this case, the dog and the couch, they are similar in the visual space, right? Because they have overlap, but they can be different in the language space. And then through using the object tag as the anchor point, they can bridge the gap between these two modalities. So as for the model input, the authors tries to represent the image text pair as a triplet. We have the word tokens, we have the object tags, we also have the regional features. And then these three kinds of input can be interpreted or considered, understood from two perspectives. One is the modality perspective, and then another is the dictionary view. This slide shows the 2D visualization using Disney. So as we can see, the OSCAR improves the cross-domain alignment qualitatively. For example, the red dots corresponding to the person, they are close in the OSCAR space, but not in this finger without using object tags. So basically, using object tags is an effective way to let the semantic gap between the image and the text modality smaller. This is another paper accepted in AAAI this year. And then in this paper, they also have achieved very good VQA performance. So the key idea is the following. In the masked language modeling, the words are randomly masked. And in this ERINE-VIL paper, which is by Baidu, the authors, they try to propose another pre-training task they call scene graph prediction. So basically, they try to learn fine-grained semantics during the pre-training. And then they argue the fine-grained semantics can be hidden inside the objects, attributes, and the relationship between the objects, which basically define the scene graph prediction task. For example, in these two images, the key difference lies in the object. And then in these two images, the key difference lies to the attributes. And then in these two pictures, the relationship between the man and the bicycle is different. So by designing this new scene graph prediction task for pre-training purposes, they then adopt a two-stream cross-model transformer network to model the general vision language representation. Based on the new designed pre-training task, they show they can learn better cross-model semantics alignment, and then in the paper they show better performance on VQA tasks and other tasks. This is a paper accepted by ACL this year, and is also by Baidu. It is kind of interesting because they ask a very interesting question: is whether we can pre-train a VLP model and a BERT model jointly, and whether they can enhance each other. And so I think this example depicted in the paper is quite interesting. So for example, in order to let a VQA model to answer this question correctly, during the training stage, it is indeed very essential that the model needs to capture some common sense or the textual knowledge from the Wikipedia. Otherwise, you can only guess, because from the image input, you do not know what's the law of the man here. So in order to support the training of a VLP model and a BERT model jointly, they have been using single image collections, single textual corpus, and joint image text pairs for effective pre-training. They have also designed a so-called cross-modal contrastive learning as another pre-training task. And as you can see from the slides, given an image text pair in the middle, they have been designed text rewriting method so that they can generate a bunch of positive image text pairs and also hard negative image text pairs. On the right side, they have also been doing text image retrieval so that they can also train the unified transformer on a single modality, and you can find more details in the paper. So this is how this model has been pushing the state of art. So for example, in the ERINE-VIL model, the VQA performance has been 75.1, and in the UNIMO model, the performance has been improved slightly further. But can the performance be further improved? And this then in the stage 4, I'm going to introduce a very interesting paper which is called VinVL, and they have been shown very strong performance on diverse vision language task. So especially the improvement on the VQA is significant. So how do they do that? So this is the VinVL paper. It's a paper in CVPR this year. So essentially, VinVL is about a much stronger object detection backbone, which can capture much richer image semantics, such as richer visual concepts and attribute information. And as you can see in this picture, the detected bounding boxes on the right side, which is used by VinVL, when compared with the bounding boxes detected on the left side, you can see on the right side, the detected bounding boxes nearly cover all the semantically meaningful regions. And as shown in this paper, this is very useful for vision language tasks. So here are some experimental results. We know visual features matter, but yet we never know it matters so significantly. It really provides large margin uniform performance improvement across many different vision language tasks by just replacing the image features. So as you can see in some example, for the VQA task, it almost provides a 3-point improvement, which is significant. For the challenging GQA task, it can provide a 3 points improvement. And they also achieve very strong performance on image captioning and the image retrieval. So the model, they are very simple. It basically provides a strong image feature. So it really can be easily plugged into any backbone that you want to try. Okay. This is basically how the performance of VQA system has been grown from roughly 65 goes to 76.6. As to how the performance has been achieved to 79, actually we don't know, but I guess it is so it must be some ensembling modeling, but we will know so in the future. Besides talking about how we push the SOTA, another interesting line of work that I'm going to discuss in the following few minutes is end-to-end pre-training, because this is very appealing approach. Traditionally, in many of the SOTA models here, basically we need to first extract the image features offline, then do multimodal fusion. But then if we can do end-to-end pre-training, this is just to say you don't need to have a pipeline so you don't need to have a two-stage pipeline, but rather one-stage model is enough. So in this direction, I'm going to talk about 3 papers, which is Pixel-BERT, SOHO, and VLT. First, let's have a brief review of how the community has studied from grid features and then transfers to regional features. And now we are going to try to shift back to grid features again. So in this seminar, CVPR 2020 paper, in defense of grid features for VQA, the authors have shown that compared with object detection, which can be very time-consuming, using grid features is very fast. And by designing careful experiments, they show using grid feature can achieve comparable performance with regional features. But then the question is why previous methods based on grid features cannot outperform the famous BOTD feature. And in this paper, the authors has identified 2 reasons. One is pre-training task, and another is input image size. For pre-training task, previous grid feature methods, they mainly pre-train the grid features through the ImageNet classification task. So this is not ideal. But by pre-training your CNN, your convolutional net on visual genome, object plus attribute detection task, the grid feature can be strong. And another is, if your image has a higher resolution, it also helps you have a stronger feature. Based on this, basically, if you so in defense of the grid feature paper, they did not do pre-training. So if you further do pre-training, then this is basically the Pixel-BERT paper. So as you can see from the finger, the supervision signal the gradient from the supervision signal can be back propagated into the CNN backbone. Another technique they introduce is the so-called random sampling. So basically it says we do not need to use all the image feature embeddings, but randomly sample some and then fed them into the following multimodal fusion part. And this has kind of the regularization effect. So the results are very strong. The Pixel-BERT achieve very good performance with a strong vision backbone. As you can see, so back then in early 2020, the VQA performance has already been pushed to 74.55. So it is very strong performance. They also show that Pixel-BERT learns very good word pixel alignment. So for example, in the top finger, dog, grass, frisbee, they all align quite well with the image pixels. As a follow-up work, the same author, they also proposed the SOHO work, which is accepted by CVPR. That's by CVPR this year. SOHO is short for seeing out of the box. Compared with Pixel-BERT, what they further introduce is the so-called visual dictionary module. Basically, instead of directly using the image features, they will do clustering. So each image grid will now be mapped to a cluster index. For example, the 2, 3, 4, 5, 9 here, and then each cluster index will corresponding to one learned image feature vector. So this is basically the idea used in the VQA model. And then in the pre-training stage, since now each image region has a label, so they design a so-called masked visual modeling pre-training task to predict the cluster label. The results are also strong. They show without using the object-centric BOTD feature, they can achieve very good performance on the VQA task. But why, right? And so the reason can be twofold. One is In this, so when they do clustering, they try to aggregate similar visual semantics into the same image space. And this is kind of trying to mimic the behavior of the object detection model. And then by doing this, rather than doing the true object detection, they can achieve faster inference speed. In their paper, they have shown that SOHO can achieve 10 times faster inference speed. And this is some visual dictionary that have been visualized in the paper. So it makes a lot of sense. For example, the first cluster is meaning about the lamp. And then the second cluster is meaning about the hamlet. And then the third cluster is meaning about cups. So the learned cluster, the learned image region, the learned image grid cluster, they capture the semantic meaning under the image grids. Okay, besides using the ResNet, besides using the convolutional nets, vision transformer is really hot. You can almost find a few papers on this topic on arXiv every day. So the same VIT architecture can also be used for vision language modeling. And as shown in this slide, in the VILT paper, which is published in this year ICML, so if you use VILT directly, it can be really very fast, because both the regional feature from object detection and the grid feature from the convolutional nets are not used. So the running time can be very small, can be negotiable compared with some heavy model like Uniter. So here's the main model architecture. As can be seen, it is very similar to VILT. Actually, the model weights are also initialized from VILT pre-trained on ImageNet classification. So basically, you send both word tokens and the image patches into the model, and through an elegant single unified transformer, you will make your prediction for downstream task. As for pre-training, following the pre-training task in previous VLP model, they have designed image text matching, mask language modeling, and word patch alignment. However, performance-wise, it is still not ideal. Take VQA as a running example. When compared with the SOTA VinVL model, there's still a 5 points performance drop. The authors have also done careful ablation studies, and then they have shown for pre-training, the longer the better. And they can also show doing image augmentation is very useful. And for Uniter kind of models, image augmentation is even not impossible because the image features are extracted offline. Here is some visualization example. As you can see, VLT VILT also learn very good word patch alignment. Okay, I think so. This is the summary. In this talk, we have walked you through the journey, how we increased the VQA accuracy from roughly 65 to almost 80, and show how vision language pre-training has played an important role in this journey. It has been spanned 4 years, and the performance has been increased a lot. So for future challenges and directions, I think there are 3 interesting topics that was further investigation. First is end-to-end pre-training. How can we close the performance gap between VLT and VinVL? VLT is appealing because its end-to-end approach is very fast. VinVL is good because the performance is strong. So how can we borrow the strengths of both, and how can we close the performance gap? Right. So some very quick answer is maybe you can try knowledge distillation, right? How we can distill the knowledge learned in VinVL for the VILT purpose. Second is the backbone architecture. Can simple MLP, such as MLP mixer, also work well when we really have large-scale image text data to conquer the model inductive bias? Besides vision transformer, MLP mixer or RAS MLP, GMLP, all this kind of model, all this kind of concurrent work, really also attracting people's eyes. So can the same idea, so for example, the MLP mixer, this kind of backbone can also be used for vision language modeling, is an open question. The third challenge, or the third question I want to pinpoint, is the human parity. How far away do we from human parity on VQA? And if this can be achieved, how meaningful it is when we say we have achieved human parity on VQA performance? And as the room for improvement becomes smaller and smaller, what's the future vision language tasks? How can we design better vision language tasks to drive the direction in the vision language field? So I think this is basically all the slides